Most energy models or building energy prediction models work reliably on cities like Dublin, Porto, or Paris, where data is clean, buildings are standardized, and retrofits are common. But for rural properties, they're different. They're older, they're more reliant on fossil fuels, and underrepresented in these models. That gap is what this research set out to explore. Could newer deep learning models outperform traditional ones like random forest regression when applied to these more complex cases? And the results might surprise you. So by way of introduction, I'm Sharon Coffey, working as a senior energy systems researcher with the UCD Building Energy Informatics Group, led by Professor James O'Donnell in the back there. And this work was done with him and also with our other colleague, Cathal, who is sadly absent today. To give you a clear roadmap of this presentation, I'll start with the motivation behind the research, walk through the key questions and approach, highlight the matters or the key matters from an engineering perspective, and also finish with the results and the closing thoughts. We know that the EU retrofit targets are quite ambitious, especially because they want buildings in the lower energy rating groups from an E to G level to be retrofitted by 2050. But the rural buildings, they are, as I say, they're sadly falling behind because of the poor ratings that they have, reliance on fossil fuels, and they're often left out of these models in the research. So the big question we asked was, how can we improve the accuracy and scalability of energy rating predictions, not just for well-studied urban areas, but also for the rural buildings that are often overlooked? And more importantly, can newer models actually help us make faster and smarter retrofit decisions in these harder to model regions? The hypothesis was simple, that advanced machine learning and deep learning models would give us more accurate predictions and scale better across building types, especially when simulating retrofits in both the urban and the rural areas. For my methodology, we kept it practical. Collect the data, in this case from Irish public data sources, clean the data, split the data between rural and urban regions, train the models, simulate the retrofits, and then compare model predictions. I'll describe each of these steps in more detail, what we went through, especially the relevant parts of the process, particularly the model training, the retrofit simulation, and the comparisons. Most literature studies used 4 broad categories, like the semi-detached, the detached houses that I've showed there on the left. But what I did was we retained the 11 distinct archetypes directly from the EPC data set that was extracted in the Irish case study to improve retrofit precision. Then we also used sub-bands like the A2 and A3 energy ratings, and not just the A. That means more accurate simulations. We also focused on where retrofitting matters most, the E, F, and G bands. And that's where the biggest gains and policy impact happen. Then, sorry, I skipped a slide, okay. The slide also shows an example of a building archetype model for detached houses. The average U values and performance data are displayed across all energy rating bands from A1 to G. And to give you a practical example, you can see how the thermal efficiency drops as you move down the bands. So if you look at the wall U values right at the top there, it starts from a 0.2 value and it drops right down to a 1.73 value for a G rating. And these are the averages we use to simulate the retrofits and predict post-upgrade EPC ratings, which gave us a more grounded archetype-based scenario and approach to modeling. There has been a significant focus on Dublin in the research conducted in the papers that I was looking at. But an important aspect of what we wanted to achieve was to emphasize the other half of the country, Ireland, which has not received widespread consideration in the past. Most literature tends to concentrate on Dublin, and because it contains the largest concentration of buildings in the country. However, there's the other half of the island for which published work is quite limited. In the Irish case study, we excluded Dublin and focused on the rest of the island, as shown by the number of properties for the urban and rural regions from that data set. Then this slide shows how the EPC ratings were distributed across the rural and urban regions. The blue line light at the top is for the rural regions, and if you look closely, you can see that the lower half there, the E1 to the G, there's quite a lot of properties in the rural regions still falling in those categories. And that's where retrofit efforts are actually most needed. In selecting the models, I wanted a balanced comparison, old versus new, simple versus complex, to see what actually works in practice. So I used random forest as the benchmark. It's one of the trusted models in the literature. It's reliable, efficient, and surprisingly accurate, even with the noisy data for environments like rural buildings. Then added neural networks, which are good at capturing the nonlinear relationships. They're relatively lightweight, but more flexible than the tree-based models. Next was a transformer, a deep learning model originally designed for natural language processing, but increasingly applied to structured data like ours. Its key strength is the attention mechanism, which helps the model focus on relevant inputs across large data sets. And then finally, I used two types of autoencoder-based regression models. Both were designed to reduce dimensionality and extract deeper structure from the data. The simplified autoencoder had a straightforward 3-layer encoding leading directly to a regression output. It was lightweight, fast to train, and aimed at capturing the essential structure without overfitting. The complex autoencoder, on the other hand, included additional batch normalization layers and a deeper bottleneck architecture. This version was designed to improve generalization by refining the latent space and stabilizing training, especially across the noisy and the varied input data. The real question was whether this added complexity could translate into better performance, and we'll look at that in the results now. Just by way of showing how a simulated retrofitting actually looks like, it was done to adjust the thermal inputs like walls, windows, and roofs based on the building type averages. So in this example, the green values on the right were obtained from the ground floor apartment in the building archetype model, especially for a D2 energy rating band. They were then used to replace the values on the left. Then we used each model to predict the EPC rating post-retrofit. The key question was how well each model performed in estimating that improvement. To evaluate the models, we used standard accuracy metrics like RMSE and R-squared to show how close the predictions were to the actual EPC ratings. And we also tracked how far off the predictions were from the real results, measured in the rating bands, and summarized how many predictions landed within the 0, 1, or 2 bands. In rural regions, the RMSE, the random forest came out the strongest with the validation and the test sets that I used. But the neural networks performed actually better on the training data. Deep learning models struggled a lot, especially the autoencoder models and more predominantly during training, where even the R-squared scores dropped far below 0. As you can see there, they're actually negative values. But they miraculously bounced back with the validation and the test sets. Now, just to give you a context, the ratio that I used was 60% for training, 20% for validation, and 20% for the test sets. In the cities, the random forest performed so much better, and it outperformed all the other models, although the neural networks and the transformer models were a close second to the random forest regression. Autoencoders again showed negative R-squared values, which could potentially happen because either the model overfitted or it was struggling to learn meaningful structure. But the test performance still improved, and especially also in the urban area. For the results, the random forest, the neural network, and even the transformer predicted most buildings within the 0 to 2 bands. That means that their results were close enough to guide the real retrofit decisions with confidence. For the cities, the neural networks predicted most buildings within the 0 to 2 bands, with random forest transformer and complex autoencoder a close second. So what does this mean in practice? First, you don't always need the fanciest model. Random forest regression remains a powerful interpretable tool, especially for rural or noisy data sets. Second, a deep learning model does hold promise, but only where your data is clean and consistent. And third, the real power is in the details. We're using granular archetypes and separating rural from urban regions gives us a more actionable, scalable retrofitting insight. Although the study was based on the Irish data set, the same approach can be applied to building stock across Europe, making it a flexible foundation for broader energy policy and retrofit decision making. Thank you.